This video is to explain the wave function psi, why it is important, and why is it useful in quantum mechanics. The best way to understand it is to look at the different atomic models used over time and to make some comparisons of what makes sense and what doesn't match up with experiment. So if we look at the most basic, we would have a proton in the center and in a circle around the electron going in a circular orbit. This treats the electron as a particle. But there are many things that don't make sense about this. One is that this is a minus charge, this is a positive charge. That would mean that you have Coulomb's law in play, and these two charges should attract each other, and there's nothing seemingly that is preventing from this minus charge to crash into this positive charge. The second thing is that you have an accelerating charge going around in the orbit. The accelerating charge releases radiation. And of course, when you release radiation, you lose energy. So the charge loses energy, and if it loses energy, it should get smaller and smaller in orbit and then eventually crash into the center. This actually should all happen in 10 to the minus 14 seconds. And it makes no sense, really. A second thing is that when we look at emission spectroscopy, when you put a tube of gas particles into a setup with an electric current to run through, you see the gas is very excited and emits light, and then if you look through a spectroscope, you'll see very defined energy levels that just don't seem to make sense when you have a circle around the nucleus. And it seems like you can draw the circle wherever you want, where a lower circle would be a lower energy and a higher circle would be a higher energy. So it seems you can draw it anywhere you want, but here it's obviously not the case. They're very defined. So we don't really get anything useful out of this picture besides the fact that the protons are inside the nucleus and the electrons are outside. Maybe we need to describe the electron as something else. And that something else, we could say, is a wave. It seems very strange at first that an electron would be a wave, but let's see what happens here if we can take a look at it. So it's not the easiest thing to draw, but you get the idea. You have a low point here, and then you go to a peak and a low point here, and another low point. So 4 peaks and 4 troughs, or low points. If you look at the physics of a standing wave of length L, this really matches up well with our conditions for a wave. This illustrates the idea of how waves behave. So if you have one mode, if you start to vibrate the string, you have a string vibrating up and down, and of course it will reflect over time and it'll start going up and down. If you want to compare the wavelength to the length, you would say that L equals lambda over 2. If you want to increase the frequency, eventually you'll get a stable mode where you have a little bit up and a little bit down. This, with your mode in the middle, or little knot in the middle, would mean that your wavelength is what lambda, 1 lambda, or 2 over 2 lambda. And if you keep increasing the frequency, you will get here, here, and here. This is 3 half wavelengths, so L being 3 over 2 lambda. And you get the idea that as you increase the frequency, you'll get a stable mode at every L equals n over 2 lambda. This makes sense when you talk about quantized energy levels from the spectroscope and the emission spectroscopy. This model explains something that the particle model is not able to explain. So you can think about an electron as a wave having to close in on itself, and only because it closes in on itself is it able to exist and not only exist, but be stable. So the wave model works very well. And the idea of the electron going around as a wave is very suitable. Another model we have to talk about is where we have an indefined distribution of where the electron could be. And this is what we would call a probability distribution. The reason why we call it that is because when you shine light onto this atom, only when you shine light do you see where that atom is. Perhaps it's there. And perhaps you leave the atom alone for a while, you do it again, and perhaps it's there, or there, or there. So it could start out, again, you could have it one time there, here, 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 and maybe a few times out here, but most of the time it's going to be around here. You get your more likely zones and your less likely zones. So here's more likely, here's less likely. How do we make use of this? If we somehow don't know where the electron will be when we measured an experiment, but we can see that's more likely to appear in some places than others. It's really weird because when we have light-matter interaction, we see the electron is a particle. It has defined spot, it has defined location, I mean. So that is odd because before we were treating the electron as a wave, and that defines these energy levels that we saw in emission spectroscopy. So we have sometimes the electron is a wave, and sometimes what we're more used to is that it is a particle. So you can ask, what is going on? And that is precisely the question that many scientists, physicists were asking as they examined this over time. One of the positions is known, say, as the realist position. And that is where the electron was always there. This was supported by Einstein because he insisted that there was a hidden variable that we don't know, that allows us, that keeps us from knowing where the electron will end up. It's not just probability. And the orthodox position, which is more widely accepted, seems to make more sense to more people, is where the electron was nowhere, but was forced to choose, or in essence, it was a wave distributed around evenly, and then eventually forced to choose one of those possible areas or locations when light is shown onto it. So today you would see electron as a wave, and then of course when light is shown onto it, then it is forced to become a particle, so to say. And the agnostic position is not very significant. You can, of course, already guess it is to refuse to answer. So not very useful. But you get the idea of what's going on and what the different philosophies behind it are. And if we were to, say, make use, if we can say make some modeling of these probabilities, it turns out that it's very useful and it leads to all the technologies we enjoy today. To get an idea of how to deal with this probability distribution, I can make a theoretical example here. We have a nucleus in the middle, and let's go back to our completely wrong, I guess, distribution of a circular orbit around the nucleus. And let's divide it into 4 zones. You have 0, pi over 2, pi, 3 pi over 2. Let's say that this is a circular path. At least you can imagine it as that. And we say that along this circular path, the electron has to be somewhere. So if we were to do this experiment, we can say we shine light onto this, and we eventually figure out that the electron is here. We shine light again, and we see that it's here this time, the second time. And then if you keep on repeating this experiment over and over again, you can see that there are more electrons here and here. according to this experiment, and maybe just 1 or 2 outside. But there are many around pi over 2 and 3 pi over 2. How would you draw a distribution function on a graph? Well, with one dimension, it's very simple to do. We can say make an axis from 0 to 2 pi. Here is pi, pi over 2, and 3 pi over 2. You'll notice that if we can say that there's a higher probability, that means that this axis is equal to, say, the probability density. In fact, we're going to call it psi squared of x. Psi squared of x being the probability density on this y-axis. And we can say, okay, it's a higher chance of being at pi over 2 or 3 pi over 2, and a much lower chance of being around pi or 0 or 2 pi. Again, we can't really say that it's impossible based on what we just saw, but we definitely know that it's a lower chance. So I would, the second thing to keep in mind is that 0 is equal to 2 pi, so this point has to be the same as this point. And we can simply draw an approximation of what we would think. Higher chance around pi over 2 and 3 pi over 2, and much lower chance at 0 pi and 2 pi. If we look at this graph, these are, say, the probabilities of finding the electron at pi over 2, finding the electron at pi, 3 pi over 2. All these probabilities have to add up to 1. That is how you make sense of mathematics of probability. All the probabilities, P of x, the summation, equals 1. You can, of course, change the summation to an integral and say that, in this case, 0 to 2 pi of P of x dx equals 1. This area has to equal 1, and that is called normalization, which we'll get to next. But just to finish off this video, I want to have the definitions very clear. Psi squared x is the probability density. You will sometimes see this in a modulus form or magnitude form because it can only be positive, being a probability density. This is useful because you will sometimes see that we deal with imaginary numbers for waves and for quantum mechanics. If you don't fully understand why, you can just say for now that we have a wave described by cosine of theta and sine of theta. And there is a very famous formula that says e to the I theta equals cosine of theta plus I sine theta. And we clearly have imaginary numbers to deal with if we were to put in this form. So this will come up more later on. And it is very fitting to call psi of x, if you were to say that we take the square root of this probability density. First of all, it's called the probability amplitude, but I want to say that it's very fitting that we call it a wave function because the electron was described as a wave in this more accurate model of quantized energy levels that fit the quantization of possible modes in standing waves. So we have this approach saying that electrons behave as waves in stable atoms. In stable atoms, the electron is a wave. And when you have light-matter interaction, then the electron behaves as a particle. And the relationship between these two and this development of probability distributions, all of this together is, in essence, quantum mechanics. So the next time we will be able to normalize this function and make sure that the probabilities of any function add up to 1.